right, now let's talk about infinite limits and what they are. I need you to pay really close attention here because we're going to get kind of technical on some of the definitions. All right, let's look at the definition of an infinite limit. Let's let f be a function that's defined at every real number. Excuse me. In some open interval containing c, except for maybe c itself. If you have the statement, the limit as x approaches c of f of x equals infinity, that means that we're going back to that original definition, which means for every m greater than 0, there exists a delta greater than 0, such that f of x is greater than m whenever the absolute value of x minus c is less than delta. And you can do the same argument for x equals negative infinity. Okay, what does that mean? Let me do a graph here. And let's look at 1 over x, which kind of shoots up like this. All right. All right. Then it goes down like this. So this is f of x equals 1 over x. Now, for every m greater than 0, there exists a delta such that if f of x being greater than m whenever x minus c is less than delta. So if we're looking at this delta region right here around 0, okay, because that's where it's undefined, then the limit as x goes to c, and in this case it's 0, is either positive infinity or negative infinity. Now please note, I'm not saying the limit is infinity, or infinity is not a number. It's a concept. And basically what this is saying is the limit fails to approach a number at c, or in this case 0. All right, let's look at this example right here. This is better than my diagram because I'm terrible at diagrams. But if this is my value m, the closer you get to m, and the closer you have this delta, the more unbounded the function appears to become. Now, notebook problems. Determine the limit as x approaches each of these for f of x is 1 over x squared minus 4. Right? Now let's discuss what a vertical asymptote is. Whenever you have f approaching infinity, plus or minus, it doesn't matter, as x goes to c from the right or left, then x equals c is the vertical asymptote. So right here in this graph, you see that as x approaches negative 2 from the left, then f of x approaches positive infinity. And as x approaches negative 2 from the right, f of x approaches negative infinity. So in this example, x equals 2 is an asymptote. And by the same argument, so is, that's negative 2, x equals positive 2. So basically, vertical asymptotes occur whenever the function becomes unbounded, when you get close enough. If you look at polynomials, or any function, if f and g are continuous, and f of c is not 0, stuff happens weird when the numerator becomes 0, and we'll discuss that. However, if f of g does, if g of c does equal 0, so finally we're dealing with situations where the denominator is 0, then you wind up with a vertical asymptote at x equals c. That didn't make a whole lot of sense, so let me explain it again. Suppose I have the function 1 over x squared minus 4. I'm going to factor this. All right, and in this case, f of x is 1. It's a constant function, that's okay. And g of x is x minus 2 times x plus 2. Now, wherever g is 0, you have a vertical asymptote. So all of the things we've been saying about, oh yeah, but denominator is 0. Now we're going to look at cases where it is. And wherever it is, you have this vertical asymptote. All right, no big problems. Turn off the video and do these. Now let's talk about properties of infinite limits. Some of these are kind of pretty much common sense. Suppose the limit of f of x as x goes to c is infinite. So this has an unbounded limit. But the limit as g of x approaches, as x approaches c, is L. So g has a limit. Let's do an example. Say f of x is 1 over x minus 1, and g of x is 2x plus 1. Just two linear functions. Then, because the limit of f of x as x approaches 1 is unbounded, let's say we're going from the positive side here, and the limit as x approaches 1 of g of x is 3. All right, then f of x plus g of x has a limit of plus infinity. And then the product of them, f times g, the limit, gives you, let's see, this is 2x plus 1 divided by x minus 1. So the limit as x goes to 1 is infinity, or negative infinity if L is negative. And the quotient rule, and this is important, remember the numerator is not 0 in this case, it's g of x. But the limit as x goes to 1 of g over f is the limit as x goes to 1 of 2x plus 1 divided by 1 over x minus 1. And I'm not going to do the algebra here, we're just going to use the theorem. And this theorem is actually 0. Now, does that make sense? What if we rearrange this algebraically? This is 2x plus 1 times x minus 1. And we see as x approaches 1, I don't have room to write it all out, this becomes 3 times 0, or 0. So it does work, even when you have functions that aren't quite so nice. Okay, do these in your notebook, turn off the video when you're done, and finish your homework. Have a great night.